This online lecture has information on the intermolecular attractive forces, and then it's going to have some practice problems at the end. So even if you know all about intermolecular attractive forces, you want to watch this because it has some you try it questions at the end. Okay, there's three different types of attractive forces between molecules. One of them is dispersion forces, and this is just that the electrons in one molecule will be attracted to the protons in another, and therefore dispersion forces increase as the number of electrons and protons in molecules increase. So we say it increases as molar mass increases. So if I look at these, you tell me which one has the greatest intermolecular attractive force, which one has the weakest. Figure it out and then restart the lecture to find the answer. Of course, this is going to be the strongest one. Why? Because its mass is going to be the largest. And then this will be the weakest. Why? Because the mass is the smallest. So this is a pretty simple idea. The largest molecule has the greatest intermolecular attractive forces. And then the intermolecular attractive forces lead to physical characteristics. For instance, this molecule will have the highest boiling point, and this one will have the lowest boiling point. And there's other characteristics that this relates to. If a molecule has a dipole moment, so it is a polar molecule, the positive end of one end of the molecule will be attracted to the negative end of another molecule. And so you can draw the entire molecule and look to see if it has the dipole, and then say, yes, it has the dipole-dipole attractive force, or no, it has no dipole, so there's no dipole-dipole attractive force. But the thing that you can remember that makes it easy is that if you see oxygen and nitrogen, or nitrogen in a molecule, those molecules tend to have large dipole moments and so have strong dipole-dipole forces. This dipole-dipole force is stronger than the dispersion force if the molecule is strong. Now, if you have a really large molecule, the dispersion force is going to be really long and it'll overwhelm the dipole-dipole force. But if it's a small molecule, these dispersion force, the dipole-dipole force can be stronger than the dispersion force and then cause a great intermolecular attractive force as a result. So if I look at this, which molecule has the greater intermolecular attractive force? Pause the lecture and then resume to find the answer. Well, if I look at these two molecules, they have about the same molar mass, so the dispersion forces are going to be about the same. But because this molecule has an oxygen and it's got dipoles, non-bonding pairs that cause the entire molecule to be asymmetrical and have a relatively strong dipole, this one will have the greatest intermolecular attractive force because it has dipole-dipole in addition to dispersion forces, and this one only has dispersion forces. If I look at hydrogen bonds, these are the greatest intermolecular attractive force between molecules. Hydrogen bonding is not a bond. That's a misleading name. A hydrogen bond is an attractive force. It's such a strong attractive force that we put dotted lines between the two atoms that are hydrogen bonding to represent that. But it's not really a bond. It's just an attractive force. If I look at this, hydrogen bonding is always going to occur between either an oxygen-hydrogen bond and another oxygen, or a nitrogen-hydrogen bond and another nitrogen. And you can have cross hydrogen bonds. For instance, water and ammonia can hydrogen bond with each other so that the oxygen-hydrogen bond could be attracted to the nitrogen, or that the nitrogen-hydrogen bond could be attracted to an oxygen. But it's always that the del negative on an oxygen is going to be attracted to the del positive on a hydrogen-oxygen or a hydrogen-nitrogen bond. This is such a strong attractive force that it pretty much overwhelms other intermolecular attractive forces. But do remember, it is not a real bond. It is much weaker than a real bond. It takes about 6 hydrogen bonds, or maybe even more than that, to equal 1 regular bond. So it's really very weak compared to a bond. It's an intermolecular attractive force. So which of these molecules has the strongest intermolecular attractive force, and which one has the weakest? Pause the lecture and select which one of these would fit those characteristics. Okay, this molecule right here has an oxygen-hydrogen bond. So because it can hydrogen bond, its attractive force is the greatest. These 3 molecules all have about the same mass, and so their dispersion forces are all going to be the same. But the mass of this one is slightly more than this one. So we can say that this molecule right here has the weakest intermolecular attractive force. Go ahead and rank the following substances in order of increasing acidity. Well, pause this and then resume after you've identified the order of acidity. If I look at these molecules, the pKa is telling us which one's most acidic. The lower the pKa, the most acidic. The higher the pKa, the least acidic. So all I have to do is put them in order of pKa, and then I have them in order of acidity. To which side does this equilibrium lie? Figure out and then resume after you figure out the answer. If I look at this, you can see this one has the greater pKa, so it's the weaker acid. Equilibrium always lies on the side of the weaker acid and the weaker base. Which one of these molecules is most polar? This is carefully look at this and think about the overall dipole. Pause and then resume when you've finished your answer. If I look at these molecules, you can see this one has some symmetry. This one's completely symmetrical. This one has the most asymmetry, 2 fluorines on one side, 2 hydrogens on the other side. Because the symmetry is the least, the asymmetry in this is the greatest asymmetry, this is going to be the most polar molecule because all the other characteristics are pretty much the same. Which of the following molecules here is nonpolar? Analyze these compounds and think about the 3-dimensional shape before you answer, and then restart the lecture. If you look at these, we have to put non-bonding pairs on the central atom. There's 2 non-bonding pairs here. Here there's no non-bonding pairs on the central atom, but there's a nitrogen with non-bonding pairs. And this side is different from this side on that central atom. If I look at the central atom here, it's got 2 different groups. If I look at the central atom here, it's got 2 different groups. This molecule has 2 groups of the same on either side, and the carbon has no non-bonding pairs. That makes this the most symmetrical of them all, and so it is nonpolar. What are the hybridization and formal charges, respectively, on the boron in this borohydride anion? Well, if I do the Lewis dot structure, pause it, and then pause it, figure out the answer, and then restart the lecture. If I do the Lewis dot structure of this molecule, I will find that that boron has 4 bonds on it. 4 bonds on an atom makes it sp3. So it's going to be one of these three. Then if we look at that, boron with 4 bonds, that would be 4 electrons on it formally. Boron has a valence shell of 3, so 3 minus 4 gives you -1. This is the correct answer. Okay, go ahead and figure out what are the other resonance structures for the carbonate anion here, and then determine what is a bond order as the number of electrons shared between the carbon-oxygen 1 bond. So pause and then restart after you've figured it out. The first thing that you have to do is figure out what is what are the other 2 resonance structures. And basically, it's that the charge and the double bonds are rotating around on these 3 carbon-oxygen double bonds. So if I look at, let's just say, this to this bond order, I see there are 1, 2 bonds here, 1 here, and 1 there. That means 4 bonds over 3 different structures. That gives it a bond order of 4/3. If I look at the equivalent resonance structure of the carbonate ion, what would be the formal charge on the oxygen? Well, oxygen 1 is, pause and then resume after you figured it out. Oxygen 1, it doesn't appear to have a charge on this one, but we know that the other resonance structures are going to have -1 charge on the 2 other resonance structures. So this gives that oxygen has 2 negative charges over 3 different structures. That gives it a -2/3 charge. And so that is the way that we figure out the formal charge that would be on that oxygen. Okay. This is a carbanion. Carbanions are carbons that have a -1 charge. In the methyl anion, the carbon is sp3 hybridized because it has 3 bonds to hydrogen, and then a non-bonding pair is the fourth area of electron density, making it sp3. Taking this into account, determine what is the hybridization of carbon 1 here. Realize there is resonance. Pause and then resume after you figured the answer. If I look at this carbon, I would see that this is in resonance with this double bond right here. There is another resonance structure where the double bond moves here and the negative charge is over here. So that any one time, this carbon is partway negative and partway in a double bond. Because it's in that double bond, it can't be going sp3 hybridization, sp2 hybridization. It must be only one of them, which is sp2 hybridized. That non-bonding pair that is on this atom right here is actually held in a p orbital that can overlap with these p orbitals that form this pi bond. That way, the pi bond can go here, and then it can go here. And the negative charge can be here and then go there, and it can do it without changing the hybridization of the atoms. That was a really hard problem because you had to kind of think a little bit out of the box. Okay, if we look at this problem, how many uncharged resonance structures exist for this? So basically, what you're going to do is try to find all the different ways that you can put these double bonds in the structure. If you look at this molecule, we can have the double bonds here shift over one just in this ring. We could have this structure, and then over here we have all the double bonds shift over one. That gives us 3 resonance structures, and it's kind of trial and error to figure it out. There's no real systematic way to figure this out. Sorry. All Lewis acids can also be classified as a Bronsted-Lowry acid. Is this true or false? The answer on this is false, and the reason is that Bronsted-Lowry acids are defined as proton donators, but Lewis acids are defined as basically an atom with an empty orbital that will accept a non-bonding pair. Sometimes they're the same thing. Because protons have an empty orbital, they can accept a base, a non-bonding pair, but they're also donating their own proton. But there are some that don't fit both definitions. Go ahead and draw an arrow to show the mechanism for this reaction. Remember, think about the bonds forming and where the electrons are going. Here, the electrons are leaving the nitrogen and reaching out to the boron to form a bond. That leaves a positive charge on the nitrogen, and then the boron gets a negative charge because it's gaining electrons through that bond. Okay, which statement best describes this reaction? Okay, if we go through these answers, you see it's an acid-base reaction, of course, because we have a non-bonding pair reaching out and forming a bond with boron. But what kind of acid and base must it be? It can't be Bronsted acid or Bronsted base because you're not having any kind of proton transfer. So these two are out. An acid-base reaction where ammonia acts as a Lewis acid or a Lewis base, that is a good possibility. Which is the ammonia going to do? Is it going to be a Lewis acid or will it be a Lewis base? If I think about it, there are non-bonding pairs here that are reaching out and grabbing the boron. Anything that's a non-bonding pair donator is a Lewis base. So the correct answer is 4. Which compound here is the Lewis acid? Well, if this is the Lewis base, you can probably guess that this is Lewis acid. But let's do it knowing that you don't know the ammonia is a Lewis base. The Lewis acid is always going to be something with an empty orbital. So if I look at the boron, it accepted electrons and became negatively charged. That means it must be a Lewis acid. Draw in the arrow to show this reaction occurring. So here's a non-bonding pair, here's a pi bond, and that pi bond is having this proton come and sit on it. So what lost electrons? Well, a carbon did because it became positively charged. Where can it lose its electrons from? One of these sets of bonds, the pi bond. So what's going to happen is the pi bond's going to reach out and grab that proton. So here's the arrow that shows that. What is the main reason why molecule A is less acidic than molecule B? Figure out which of these is the correct answer and then resume the lecture. It is not because there are more hydrogens in A, because all of these hydrogens are being held covalently. So these can't be more acidic just because there's more. The carbon-hydrogen bond is weaker than the oxygen-hydrogen bond. Is that the reason why? No, that's not the reason why. They really do not have that great an energy difference. There's something much more important than the strength or the weakness of the oxygen-hydrogen bond. If I look at 3, the conjugate base of A is more stable than the conjugate base of B. If that were true, then A would be more acidic, not less acidic. The conjugate base of B, the negative charge resides on a more electronegative atom. Ooh, that sounds really good, doesn't it? Let's look at the last one and choose 4 if this isn't any better. There is resonance and inductive stabilization of the conjugate base of B. Well, if you look at the inductive stabilization, that would mean there would have to be electronegative atoms on this end of the molecule to stabilize the negative charge here. That's not happening. There's no resonance either because why? There's no double bonds. So the good answer is that one right there. Okay, intermolecular attractive forces determine the shape and property of biological molecules. Which one of the following do not play a role in intermolecular attractive forces? This is an easy question if you've paid attention to the online lecture. This is the only thing that is not an intermolecular attractive force. Of course, magnetic forces are with only a few atoms like nickel and iron, and between, let's say, two electrons. When we're talking about molecules, these first three are the only intermolecular attractive forces that we see in that are important in biological molecules or any molecules. So which is the correct order of the pKa values of these species here? Figure out which order is correct and then resume the lecture. Okay, if I look at these molecules, I can put them in order of acidity quite easily. And once I put them in order of acidity, their pKa values are going to decline as they become more acidic. So if I look at the least acidic of any of these, it's going to be hydroxide. The next acidic is going to be water. The most acidic is going to be the hydronium ion. So this is the order of acidity, and so the pKa would be highest for this species and lowest for this, because this would be most acidic. Okay, look at this equilibrium and determine which statement is incorrect. Pause it and then resume when you figure out your answer. Okay, in determining the answer to this, first thing you'll do is look at pKa 10, pKa 16. This is the weaker acid. This is the stronger acid. The equilibrium is going to shift to the weaker acid. So that means the equilibrium will favor the products. Water is a conjugate acid in this equilibrium. Well, water is a conjugate acid of hydroxide. Hydroxide is the strongest base present. Well, let's look at that. This is a stronger acid. This is a weaker acid. So if this is a weaker acid, that's going to be the stronger base. So hydroxide is a stronger base than phenoxide. Phenol is 6 times more acidic than water. Well, that's incorrect because the pKa are representing powers of 10. So it's not 6 times more acidic, it's going to be 10 to the 6 times more acidic. And then the negative charge on phenoxide is resonance stabilized. Well, a negative charge on a pi system will have resonance, so that is true. And so this is the incorrect answer. Okay, which of the above structures is not a resonance structure of the others? In order to determine this, try using your arrows to push the electrons around to see if what you can do to make one structure into another. Pause it, try to figure it out, and then we will go through this. This actually is the answer, and let's go through why. This is the first structure. I'm going to move the arrows to push the put the arrows in to push the electrons around, and you see I can get this structure. So this one is a resonance structure. I can take this structure right here, and I can push the electrons around to make this one. So it's a valid structure. I can take this structure here, which we already verified is 1, and I can move the electrons over here like that to form that one. This is the only one I can't do that. Notice also that the pi bonds are not conjugated. There's a gap right here where there would be a hydrogen attached. So on all of these, you have hydrogen, 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 2 hydrogens. And if you go around and check each one of these, you would find the same number of hydrogens on all these structures until you get here and see there's no hydrogen here, but there has to be a hydrogen here. So this one can't be because it actually has an extra hydrogen here on this atom, which can invalidate